Let's understand everything about the one sample t-test. So in this one, I will explain what a one sample t-test is, when it is used, and some example use cases of where you could use this test in real life. Once you have that understanding, I will walk you through the procedure of performing the t-test with a full-fledged hand computation without using the computer. If you are just given the raw data, how to perform the t-test by hand. We will see how to do that. And finally, the same hand computation, instead of doing it mathematically by hand, we will do it step by step in the R programming language with and without using the built-in t-test function. So the results that we will produce will exactly match with the results of the t-test function that you can use directly to perform the t-test. The reason to do it step by step is you will really understand what is going on behind the scenes, and none of the statistics terminologies will remain unexplained in the back of the head. So let's go right into it. So the one sample t-test was first invented by William Seeley Gossett in the year 1908, which means this test has been around for more than 100 years. And since he used the pseudonym student when he published the test, it is also called the student's one sample t-test. Now, the primary purpose of performing the one sample t-test is to test if a given sample's mean is equivalent to a hypothesized population mean. To put it in more simple terms, you are given a sample and you want to test if the mean of that sample is actually equal to one particular value, and this value is nothing but the population from which this sample that you have at hand was supposed to be drawn from. We will see more examples on this. Now, in the t-test, the test statistic is assumed to follow a normal distribution, and because of this it is considered as a parametric test. And in most t-tests, the test statistic is nothing but the sample mean itself. Let's see a possible use case. A customer service company wants to know if their support agents are performing on par with the industry standards with respect to the mean resolution time. According to an industry report, the standard mean resolution time is 20 minutes per ticket. Now, this company took a small sample of 30 agents and they measured their mean resolution time to stand at 21 minutes per ticket. And for these 30 agents, the standard deviation of the resolution time was 7 minutes. With this data, can you tell if the company's performance is different from the industry standard or not? Let's see another example. A farming company wants to know if a new fertilizer has improved the crop yield or not. Now they have the historic data, and the data shows the average yield of Bengal potatoes is at 20 ton per acre. They decide to test a new organic fertilizer on a small sample of farms, and they observe that the new yield stands at 20.175 tons per acre, and the standard deviation is at 3.02 tons. Now, since they tested it on 12 different farms, the sample size here is 12. Can you find out if the new fertilizer worked to make any change in the crop yield or not? We will further use this example to do the hand computation. Let's understand the general procedure of performing a t-test. Now, the first step to do a t-test is to establish the null and the alternate hypothesis. Now, the null hypothesis is usually represented as H naught, and the hypothesis is that x bar equals to mu, which means the sample mean equals to the population mean. The alternate hypothesis usually negates the null hypothesis. So it states that the sample mean is not equal to the population mean. The second step in performing the t-test is to compute the t-statistic, where the t-statistic is nothing but x bar is the sample mean, mu is the population mean. This is the mean that we are hypothesizing. This is the sample's standard deviation, and the root n is the number of samples we have. This whole term in the bottom is nothing but the standard error. The next step is to compute the critical value. Now you know the value of t, you need to look it up in the t tables. What should be the critical value for t for a given significance level and for the given degrees of freedom that we have for our data set. So that is one way. The other way is you can directly compute the p-value of the computed test statistic. And this p-value depends on the number of degrees of freedom as well. Now the degrees of freedom is nothing but the number of coordinates by which you can freely change the values. So in this case, there are 12 different forms and you have a given t statistic. Given this situation, you can change 11 different forms values. So the degrees of freedom here is 12 minus 1 equals to 11. We will shortly see how this degrees of freedom affects the critical value as well as the p-value that we are computing. So once you know the p-value, if the p-value is less than the significance level, which is usually 0.05, then you reject the null hypothesis. Now the null hypothesis is the sample mean equals to the population mean. If the p-value is less than 0.05, you reject that and conclude that this sample that you have at hand is not representative of the population. Alternately, if you have the critical value, if the absolute value of the critical value is greater than the computed test statistic, that is, if t critical is greater than the computed t that you have from this formula, then also you reject the null hypothesis. While doing the hand computation, I will explain the reason as to why we reject the null hypothesis when critical value is greater than computed t statistic, as well as why we reject the null hypothesis when p-value is less than 0.05. Now let's go to the hand computation.